Hello, welcome to Basics of Finite Element Analysis. In the last lecture, we had started discussing the Euler-Bernoulli beam, and we had covered basically its theory and the differential equation, and we had also discussed in somewhat detail about our conventions related to what is positive in the sense of the primary variable, and we also made a point to state that in case of an Euler-Bernoulli beam, there are at each point there are 2 degrees of freedom. The first degree of freedom is the deflection of the beam, which is W, and the second degree of the freedom is the slope of the beam, which is negative of partial derivative of or derivative of W with respect to x. So, today we will go one step further, and our aim is that we want to develop ultimately element level and then assembly level equations for this beam. But before we do that, we have to develop interpolation functions for the beam. Now, we cannot use the standard Lagrangian functions for beams, because at each node there are 2 degrees of freedom, and they are related to same physical thing, which is the displacement W. So, if I use the Lagrangian formulation, then it will not work out. So, that is why we have to develop a new set of interpolation functions, and we will develop in context of a 2-noded linear element, and whatever we develop in today's lecture, we can extend it to a quadratic element or a cubic element and so on and so forth. So, our aim is to develop interpolation functions. Okay. So, before we start doing that, we will again review that our degrees of freedom. So, suppose I have an element, this is node 1, this is node 2, let us say the length of the element is HE, the local coordinate system is such that this is x bar and the value of x bar is 0 here and HE here. Then my 4 degrees of freedom are W at 0, and this I call it as W1, and I will use a generalized term for this, and I will call it as U1E. So, U is a general notation for a degree of freedom. The second degree of freedom is slope at 0, and it is not just the slope, it is negative of slope, right, and this is equal to some angle theta at location 1, and this I will call it as U2E. So, I have U1 and U2 located at node 1, 2 degrees of freedom at node 1, U1 and U2. Then my third degree of freedom is W at HE, which is the node 2, and this is equal to, physically it is deflection at point 2, and this I call as U3E. And then the last one is slope at node 2 of the element, and this is physically some angle theta 2, and this I call it as U4E. So, at node 1 I have U1E and U2E, and node 2 I have U3E and U4E. U1 and U3 are translational degrees of freedom, u2 and u4 are rotational degrees of freedom. So, now we say that w in the is the displacement, it is a function of x, and this equals uj e times some approximation functions j equals 1 to, and in this case there are total 4 degrees of freedom. So, we will say 4. So, this is u1 e times phi 1 of x plus u2 phi 2 of x plus u3 phi 3 of x plus u4 phi 4 of x, and because I am having a local coordinate system, I will actually make them x bar, and also because this is all related to eth element, I will have a superscript e for all the terms. Okay. So, here phi 1, phi 2, phi 3 and phi 4 are the approximation functions, and our aim is to develop these approximation or interpolation functions, which we right now do not know. Now, if you look at these approximation functions, you will see that u1 explicitly comes in phi 1, u2 explicitly comes with phi 2 and so on and so forth, right. And this w has to be, w represents the deflection over the length of the element. Okay. So, the nature of w is such that w at 0 should be equal to u1, right. So, these are the conditions, we have already written them. W prime should be equal to u2. So, I am just rewriting those. W at he should be equal to u3 and W prime at he should be equal to u4. So, we have just written these conditions which we stated earlier. Now, please note that these conditions, these are the boundary conditions for the specific element, right. These are the boundary conditions. They have to be always true, because u1, u2, u3 represents their degrees of freedom, they have to be all. And these x's, the length of the element could be anything. So, for all values of x, these conditions have to remain true, and this will be true only if we have these following conditions satisfied. So, this is these BCs, this is u4, oh this minus should be there. So, these BCs will be satisfied regardless of he and specific values of u1, u2, u3 and u4 if the following conditions are held. What are those following conditions? So, there are 16 conditions, and once I write them down, it will make sense to you. So, this should be x bar is equal to 0 and x bar equals he, and phi 1 prime, phi 2 prime, phi 3 phi 3 prime, phi 4 and phi 4 prime. So, I am actually making a table. Okay. So, at x is equal to 0, phi 1 should be 1 and phi 1 prime should be 0, everything else should be 0. Then at x is equal to 0, phi 2 should be 0, its slope should be minus 1 and phi 2 and its slope should be 0 at HE. Then at x is equal to 0, phi 3 should be 0, slope should be 0, but phi 3 should be 1 at x is equal to HE, but its slope should be 0. And finally, phi 4, it should be 0 and its slope should be 0 at x is equal to 0, and also it should be 0 at HE, but its slope should be minus 1. So, if we have these conditions, if we can somehow enforce these conditions while choosing phi 1, phi 2, phi 3, then all these conditions will always be satisfied. Okay. So, now we will develop 4 different functions, phi 1, phi 2, phi 3 and phi 4. So, let us say phi 1, and because it involves 4 degrees of freedom, because we have 4 degrees of freedom per element, so it will have 4 terms, and let us say this is equal to A plus B x bar plus C x bar square plus D x bar cube, and we do not know A, B, C, D are unknown. A, B, C, D are unknown. So, to find A, B, C, D, we use these conditions related to phi 1. So, we get 4 equations related to A, B, C, D and we get 4 unknowns. So, we will write down those equations quickly. So, phi 1 at 0 equals 1, and this, when I put x is equal to 0, I get A. Okay. The second condition is phi 1, its derivative at 0 equals 0 and this is equal to B. If I differentiate phi 1 and put x is equal to 0, this is what I get. Third equation is phi 1 at HE equals 0 and this equals A plus B times HE plus C HE square plus D HE cube. This is the third equation. And the fourth equation is phi 1 HE, its slope is equal to 0 and this is equal to B plus 2 C HE plus 3 D HE square. So, from these 4 equations, these are all linear equations in A, B, C, D. I can very easily solve these for finding out values of A, B, C, D. So, what I get is A is equal to 1, B is equal to 0, C equals minus 3 divided by HE square and D equals 2 by HE cube. So, ultimately what I get is that phi 1 of x. So, I put all these values of A, B, C, D. These values of A, B, C, D, I put it in this equation and I get my expression for phi 1 x. So, my phi 1 x is equal to 1 minus 3 x bar over HE whole square plus 2 times x bar over HE cube. Yeah. This is how I get my phi 1. Similarly, I can calculate the nature of phi 2 from these 4 conditions. I just write the same expression for phi 2, use these 4 conditions, I can get new values of A, B, C, D, and I will get phi 1. Then I can get another set of conditions to get the expression for phi 4, and then a 4th set of conditions to get expression of phi 3 and phi 4. Okay. So, my 4 approximation functions using this method, I will write them directly. So, this is for each element is minus x bar 1 minus the whole thing square phi 3 x bar equals 3 So, these are my 4 approximation functions, and I call them, these are not Lagrangian functions, they are significantly different, and I call them Hermite functions. So, I call them Hermite functions. Okay. And if we verify, we will see that phi 1 is such that its values are like this, and same thing for phi 2, phi 3, phi 4. Okay. So, if I use these functions, 4 functions in my expression for W, then I get what I wanted to have. Okay. So, here instead of using Lagrangian functions, interpolation functions, which we had used in context of second order ordinary differential equation, for 4th order, because at each location we have W and W prime as primary variables, I have to use a different set of functions known as Hermite functions. Now, these functions are valid for a 2-noded element, but I can construct a 3-noded element using same theory, and I can have a new set of Hermite functions. In a 3-noded element, I will have, because I have 3 nodes, at each node there are 2 degrees of freedom. So, total degrees of freedom is 6. So, because of that I will have 6 Hermite functions, not 4, and so on and so forth. So, in that case it will be, I will have 2 more terms, a quartic term, that is x to the power of 4, and a pentic term, x to the power of 5 also. If I plot these functions, then these plots look something like this. So, let us say this is my normalized x. So, minimum value is 0 and maximum value is 1, and on the vertical axis I am plotting the value. So, this is 0 and 1. So, my phi 1 is 1 at x is equal to 0, and it becomes 0 at x is equal to 1. So, that is my phi 1, and phi 3, which is the other, which is the deflection at the second node, its value is 1 at here and 0 here, and this function looks something like this. So, this is phi 3. If I plot the slopes of phi 1 and phi 3, they will be 0 at both the ends, because that is what our condition was. The slope of phi 1 at both the ends is 0, and slope of phi 3 is also at both ends, it is 0. So, if I differentiate these functions and I plot the slopes look something like this. and that is phi 3 prime and this is phi 1 prime. So, the contribution of the slopes at the nodes is again 0. And then we will draw another set of curves for phi 2 and phi 4. So, that is my normalized x axis, maximum value is 1, minimum is 0, and if I so this is minus 1 and the slope of phi 2 is minus 1. So, this is 0 and so this is phi 2 prime and this is phi 4 prime, and the actual value of these functions phi 2 not their slopes is something like this. So, this is phi 4 and this is phi 2. Okay. So, this is the nature of Hermite functions, and so this is phi 4 prime. So, these are again these are known as Hermite functions, and these are the functions which we will use for developing finite element equations for an Euler-Bernoulli beam. So, that is the exercise which we will do it in our next lecture, and this concludes our discussion for today. Thank you very much.